There is Shubham Chandak, who's from Stanford University, who's going to talk about Spring, which is a next generation compressor for FastQ data, who works very well. Thank you.
Hi. Yes, I will present a compressor for FastQ data. So just to get a sense, like FastQ data is the raw sequencing data, and I will talk about that very soon. So this is joint work with Kedar, who is at Stanford, Idoya and Mikhail at UIUC, and Saki, my advisor. Okay, so I will start with the introduction and some motivation, although I think the motivation should be clear in this session. Then I will go to the FastQ format and present some results, followed by the algorithm. So I will talk about Spring, and I will also briefly talk about the other approaches for FastQ compression. Then I will briefly talk about Spring as a tool, and finally I will finish with the future work, next steps. So what is genome sequencing? Like, what is the model we are working with? So I will mostly be working with Illumina sequencing. So where so you have the genome. So for example, the human genome is 3 billion bases long, and you get these paired end reads. So each read is roughly 100 to 150 bases long, and the pairs, like the end-to-end distance of the pairs is around 300 to 500 bases. And the reads might have some substitution errors, although it's 1% or lower. And finally, the one quantity is the coverage, which is the average depth. So at each position, how many reads do you get roughly? Right. So with this model in mind, that's right. So how do we use these reads? So like the two most common workflows that I know of are, so one is like if you already have a reference for that particular organism, then you align it to the reference, you do variant calling, and finally you get like the difference of that data set to the reference. And another workflow is the assembly, where you don't, like you sequence a new organism and you just want to assemble the genome. Right? So like the big question is, why do we need to store the raw reads? Why don't we just like go to the final thing, like the VCF or the assembled genome? Like ultimately, that's what we care about. So why do we want to store the raw reads? So here are some possible reasons. So one is like all these pipelines, the alignment, variant calling, assembly, they keep on improving with time. Every year you get a new version. And ideally you want to store the raw data so that you can do the reanalysis. Even for temporary storage, like the alignment and assembly are quite time consuming. So even for like storing it temporarily, or maybe you want to store it for some time, so maybe you want to compress it. Sometimes you don't have the reference genome, or it's not really like just single organism, you have metagenomics or some such application where, again, storing the raw data might be useful. And finally, and this is quite interesting, sometimes you can actually get better compression even though you have a reference, and if you align to the reference and do like the aligned data compression, you can sometimes get better compression if you don't even use the reference, and we will come to this later. So hopefully this is enough motivation for why we want to compress FastQ data. So let's look at what the FastQ file looks like. So since we have paired end reads, so we get two files, file 1, file 2. So the records are stored in 4 lines. The first line is the read identifier, followed by the actual read. So read identifier is just some data about the lane number, flow cell, or like some information about the sequencing. The read is the actual substring from the genome with some substitution errors. Then you get a plus sign, and then you have the quality values, which William talked about earlier. So quality values represent in ASCII the confidence of the base caller about its base call. So for most of this talk, we will focus on reads. I will briefly talk about the qualities and read identifiers. So let's talk about read compression. Right. So let's say I take a typical 25x coverage human data set, and I just look at the reads, like the ACGT symbols. If I don't compress it at all, it takes around 79 gigabytes. Now if we use like the standard gzip, so what I observed was like gzip usually just compresses it to roughly 2 bits per base. which is like ACGT, you have 4 symbols, so you actually need 2 bits per base if you use like the naive encoding. And the question is this optimal? So it's not, because you have very high coverage, so you have lots of reads from the same region of the genome, so there is a lot of redundancy. So ideally, you should be able to do better than this. Another question. So as I said, like you get these reads as pairs from the genome, and the order of these reads is not really that important because it's just due to some randomness in the sequencing process. Of course, the pairing of the reads is important because the pairing tells you that these reads were close by in the genome. So if you have this reads in the FASTQ file in some original order, what if you reorder these pairs? So the pairs are still intact, but you reorder them. Can this also save some space? So let's look at some results. So again, we see the uncompressed and the gzip size. So FASTOR is like the previous state-of-the-art compressor, which is like a specialized compressor for FASTQ files. And in the mode where it allows the reordering of the pairs, as I mentioned before, it reduces it from 20 gigabytes to 6 gigabytes. Now, if you look at the results for Spring, even if you allow no reordering, so it's like lossless, it's still 2 times better than FASTOR in the, like when it allows reordering. And when you do like the comparison in the same mode, it's as much as 3 times better on this 25x database. And like if you look at like between the gzip and Spring, it's as much as 10 times better, or 6 times better in the lossless mode. And as you go to higher coverages, like the gap between FASTOR and Spring reduces, but it's still quite significant. Like in the same mode, it's still around, 2.5 times better. And of course, like as compared to gzip, it's very, very good. And so what's the main idea behind Scream? How do you compress these substrings? So, and this is not like nothing new, but let's go through it. Right. So when you're storing reads, what are you really storing? So in a sense, you're storing the genome. You're storing the positions of the reads in the genome, and you're storing this gap between the pairs. And finally, you are storing the noise in the read, like where does the read differ from the genome, right? So if you store these 3 things, you are basically storing the reads themselves. And you can do some sort of theoretical analysis, some entropy calculations, and you can show that if you are able to do this, you can actually outperform many of the existing compressors. And like this is nothing new, like this is being done in the aligned data compression all the time. But for raw data, the big question is like, how do you get the genome from the reads? Right? Because like assembly is very expensive, and like we talked about, like first you want to store the data for some time and then do the assembly, but if you want to do the assembly for the compression, that doesn't make much sense. And why is the assembly very expensive? Like 2 main reasons are like you need to resolve those repeats, and you have these low complexity regions, and you want like very, very long pieces of the genome. So what's the solution? The solution is like for compression, you don't really need perfect assembly because assembly is not our aim. Our aim is just compression. So we can like make do with some sort of approximate assembly. So let's look at what Spring does to the reads. So you start with these reads. You do some type of approximate assembly, which I will talk about in the next slide. And what you get are these reads, which are like overlapping reads. And these red portions show that like the read does not match with the others. And what you do is you take these reads, which are sort of overlapping with each other. You take the majority vote, and you make these approximate assemblies. And you don't expect to get whole chromosomes as you might want in an assembly application, but you still get like very long pieces. And after this is done, then it's like, as I said before, you need to store these green things. You need to store the read positions in the assembled sequences. You need to store the gap between the paired reads. You need to store the noisy bases, the positions of those bases, all these things. And finally, you use like a standard entropy coder. So BSC is a BWT-based compressor, which works quite well. And you get your compressed file. So if you remember, I said earlier that if you allow the reordering of the pairs, you can actually improve the compression. So where do we improve? Like the assembled sequence remains the same. The gap between paired reads remains the same. The noisy basis positions, that remains the same. The only thing is this read position. What you do is you basically reorder the reads according to their position in the genome. So now it becomes an increasing sequence, and then you can do delta coding, and that improves compression quite a bit. So let's look at the first step. So again, like this approach has been done by other works. I think like the main improvement by Spring is due to the very good approximate assembly step. So let me talk about that. So what we do is we index the reads by some substring in the read. So we build a hash table which maps a substring to the reads that contain that substring. And then for each read, we try to find overlapping reads which are very similar to this read. So let's look at a simple example. This is simplified example, does not represent what actually happens, but still. So you have a read, and you have this green, this blue thing is the index. Like the read has been indexed by the prefix. Right now you look in the hash table. Maybe you find another read which has the same index, but it's like very different in the other positions. So we don't use this. Right, so it's the Hamming distance is too large, you shift. So what you do is you shift this search substring by 1. Now you look again in the hash table. Maybe you don't find anything. So you shift again by 1. This time you find a read which matches it and which is very close in the other positions as well. Good. So we found the next read, and then you repeat this process with the new read. So like you get, sorry. Yeah, like in this way, you get this sequence of reads which are overlapping with each other. And if at some point you don't find any match, you just give up and then you start with a new read. So that's why you get these breaks and yeah. Right, so this is like the important step where Spring achieves most of its improvement. So let's talk briefly about quality and read ID compression. So for quality, we basically use just BSC directly and optionally applying some quantization steps. We also have the option of supporting QVZ, which was developed by Idoya and Mikhail. For read identifiers, we basically split it into tokens and use arithmetic coding. So for these two, we don't really do anything new. It's just standard. But let's look at the results. There are a few interesting points. So one thing is if you compare like the older Illumina technologies like the HiSeq and the new ones, NovaSeq, and like comparable coverage, you see like the contribution of the quality values. So these are the compressed sizes in gigabytes. The contribution of the quality value has drastically reduced in the newer machines because earlier they used to have 40 levels of qualities, now they have just 4 levels. And now therefore like the contribution of the reads is much more significant as opposed to earlier. So that's why the Spring achieves great improvements in the NovaSeq datasets. Another interesting thing, if you go to the allow reordering mode, where you allow the reordering of the pairs, as I showed before, the size of the reads decreases, which is expected. But you see the size of the read identifiers actually increases. And why is this happening? Because like in the FastQ file, you can actually, looking at the read identifiers, you can actually find the order of the reads because it's in some increasing order. So in a sense, the read identifiers contain the information about the ordering. So even if you reorder things and if you store the read identifiers, you have not lost any information. And that's why only the loss here goes here. And so it does not make sense to like do the reordering and still store the read identifiers. Like you should ideally then discard the read identifiers if you want to go to this mode, the allow reordering mode. Yeah, so this is what I talked about earlier. So let's compare Spring versus a reference-based compression. And this is like just for illustrative purposes. It might not happen in all cases. So we start again with the same 25x file, 195 gigabytes. We use Spring. In 2 hours, you get a 7 gigabyte lossless file. Now, if you do alignment, which takes 8 hours, so everything is, I think, running on 8 threads or like same number of threads. You get the SAM file. You remove the fields which are not really needed to get back the FastQ. Then you optionally do sorting. And then you use like one of the best compressors for SAM files, CRAM. And I use the options with the maximum compression. So this is much faster than Spring. But the results, if you see, like if you do the unsorted file, it's slightly worse than Spring, similarly for the sorted. And if you actually embed the reference, then it becomes, so you see Spring is actually doing slightly better than if you do the alignment and the whole process. And this can be due to various reasons, partly due to read compression, maybe due to quality compression, perhaps the entropy coder is better, but like we get a sense that actually sometimes just doing a reference-free compression can give better results. And of course, this advantage can be even greater in case there are large variations between the reference you are using and the FastQ file. So let's briefly talk about some other approaches for FastQ compression. So of course, like the most commonly used approach is gzip or bzip2, which hopefully people will move away from very soon. Then there are multiple works on context-based arithmetic coding-based approaches. And so gzip and bzip like don't even separate the reads, qualities, IDs, but here they at least separate it, and then they use specialized compressors, arithmetic coding-based. And these are very good in terms of speed, but the compression, while much better than gzip, is not as good as the tools I will talk about. There are a few which are assembly-based, where they try to, which are very similar to what we are doing, but they use different approaches. Then there are some which are like reordering-based, where they use, so many of them actually do clustering based on some common substrings in the reads. So in particular, ORCOM, MINS, FASTOR, all these actually do like based on some substring of the read. So they collect similar reads and try to do something similar to what we did. So these were all before Spring. Let's look at some things that came after Spring. So it has been a year, I think. So there was one called Minicom, which uses similar approach to some of the earlier substring clustering-based approaches, but they tried to make like much larger clusters, and they actually have slight improvement over Spring on RNA-seq datasets. Then there was another work called FQ Squeezer, and this was very interesting because they actually used just general purpose compressors. They didn't do any assembly, anything. And still they see 10 to 30% improvement over Spring for smaller bacterial data sets, which is, I think, very interesting. Unfortunately, both of these are like many times more like time and memory intensive than Spring. It's like around 10 times more time and memory. And so they did not really test on like human data sets. They tested only on very low coverage human data sets. So yeah, but in the future, we might see something even more interesting. So let's talk briefly about Spring as a practical tool. Right, so this is what it looks like. So you start with this 195 gigabyte 25x human FastQ. In 2 hours time with 8 threads and 32 GB RAM, you get this 7 GB file, which is around 5 times better than what you get with gzip. So this is the whole FastQ file, not only the reads. And then decompression is relatively faster and needs lesser RAM. And then you get back the exact same FastQ file. So this is lossless compression. Right. So like the one big bottleneck right now is this RAM consumption during compression. But this is shared by many of the assembly-based ideas. And yeah, so this is one of the things we can work on later. So in particular, like on the whole FastQ file, we get 1.6x better compression than FastOR. And note that like for quality and IDs, we are using basically the same thing. So we don't get any improvement there. All the improvement is in the read compression. Right. And also Spring is like relatively easy to install, use. It has like lossless and lossy various modes. It supports variable length reads. Many of the previous compressors did not. We also put in a special mode for very long reads where like our read compression is different. We just use like standard BSC compression, but at least it supports it. We allow random access. So if you want like just some part of your FastQ file back from the decompressed data, you can get it back. Spring basically compresses things in blocks. And it is scalable to large data sets up to 100x human genome we have tested. It is available on GitHub. So some of the next steps we are working on right now, we are integrating Spring with Genie, which is an open source MPEG-G codec. Hopefully that will help improve its adoption further. Some of the interesting ideas for the future. So one I think is working on 3rd generation sequencing technologies like nanopore. So they have like long reads, lots of insertions, deletions, and the ideas I mentioned that work for Spring, the hash-based ideas, don't really translate directly. So we need some new ideas for these. And we also have new types of raw data, which take much more space than the reads themselves. So we have the raw current signal, for example. And right now, people are still storing all the raw signals because the base caller for nanopore is improving every year. So I think this is quite important. Another thing, this is more for the Illumina side, like getting time and memory efficient tools with compression very close to Spring. One idea could be, I don't know how to do it yet, but like using some disk-based strategies. So some of the previous compressors, they needed very less RAM because they stored things on temporary files. So that might be something to do. And one thing which was suggested by a reviewer, I think, was like when you have a reference available, maybe you can actually use some information from the reference. Like you don't need to completely work with the raw data itself. So like do the best of both worlds in some sense. So yeah, thanks.
Very nice. You touched on random access and you touched on the time for decompression. Have you considered implementing some kind of search within the compressed file? It seems like you have these approximate contigs. If you could kind of search on those and then extract the reads associated that hit those parts of the config, you could do some kind of search within the compressed file. Have you considered that?
Yeah, so we have not really thought about that, but yeah, it might be possible. Maybe you mean like some K-mer-based search,
Yeah,
right?
something like that.
Yeah. So we have not thought about it, but yeah, it might be something to look at. Yeah.
I also have a question about random access. A lot of sequencing assays now produce barcodes along with the reads for various things. The ones like for single cell assays or whatnot. Personally, I'm using linked reads, genomic linked reads, where each read has a barcode. So for the random access, I'd love to be able to pull out all the reads for a given barcode. So I was just wondering if that's something that Spring does now or if it's something it could do.
So right now it does not, but I think we actually talked about doing it at some point. Yeah, so that's also part of the things.
Great, thank you.
Hello, thank you so much for that lovely talk. I was especially impressed with how fast Spring is compared to doing, say, an alignment and then doing alignment-based compression. I was wondering, though, you're in some sense comparing approximate assembly for compression against a attempt to be highly accurate with BWA mem for your mapping and then doing a reference-based compression. What happens when you compare instead against something like Snap, so a faster, not accurate aligner, just for the compression step, not necessarily because you want to actually do alignment?
Yeah. So I think that's like similar to what I told, like this last step. If we can do fast and approximate alignment, I think that, I don't know if it will improve in terms of compression, but I think in terms of speed, it might be much faster. Yeah.
So I had much the same question, but thinking from the assembly side, actually, is that when you say BWA takes 8 hours, no, sorry, not BWA, actually whatever it was, something took 8 hours. But have you looked at Miniasm? Because that's one of these sort of like really fast, quick and dirty assemblers that doesn't really give you the accuracy of some of the slower assembly programs out there, but is that comparable to your assembler? I mean, what is it that makes your assembler so fast compared to these other things?
So I think one thing is we don't worry at all about repeats or any of these things. Like if you have repeating regions in the genome, in our assembly process, they all come together. We don't care about that. So that's one big thing. Second, like during the assembly process, we don't look at the paired end information. We just think of it as single end. So again, that saves us a lot. I think like those are the big two things. Okay. And plus we are like only looking at Hamming distance, so we don't worry at all about like any indels or anything, which works quite well for Illumina data.
Yeah, it's certainly impressive, and I'm sort of pleased that this wasn't around when the sequence squeeze competition was happening, because I think it would have won. Yeah. Thank you.